All right, Andy, I make it 10 o'clock. So why don't we get started with this morning's session?
Yes, great. Thanks, Maria. So my name is Andy Rivenes. I'm a product manager for database and memory, and we have Maria Colgan along with us, the SQL Maria, and so she's a product manager and evangelist for all things Oracle database. I actually did want to remind you, people or folks that are watching, that so this is the fourth session that we've done, and you can get to these sessions. I have the URL page up here. We did configuring the column store, why our column store scans faster, and join performance, and those are actually recorded as well as this session. So that's just on the public URL for database and memory office hours for AskTOM. So anytime you want to go back and look at any of our previous recordings, and we're actually to some extent building on previous or our new sessions are building somewhat on some of the previous ones. So it may be valuable to go back and take a look at this if I happen to mention that, well, we talked about that with hash joins, or we talked about that in configuring the column store. So those are resources for you that are available to go back. And with that, today we were going to focus on aggregation, so essentially group bys, because database and memory can leverage aggregation or group bys and take advantage of certain features within database and memory to significantly speed up aggregation. And with that, we'll skip over our safe harbor statement, although we're not really talking about anything particularly new. In-Memory Aggregation and has been available in Oracle database and memory since 12.102. So we keep enhancing it. We'll talk a little bit about some of the enhancements that we've done, but it's a core piece of database and memory functionality. So I wanted to kind of review what a group by was or is. So in case, kind of like we did with hash joins, in case you may not be completely familiar with the ins and outs of group bys, but basically we're talking about aggregating one or more columns, if you will, around and aggregating the total number of rows associated with those columns. Kind of my lame or layman's way of explaining that. Not lame necessarily, but layman's. But I basically copied some selections out of the documentation that try to explain exactly what a group by is. Again, aggregate functions like mins, max, counts, anything where you might sum up or look for total values over a group of rows based on one or more columns that you're going to do the grouping by. There's actually two group by types in Oracle. Originally sort group by, and that's been around since the beginning of Oracle time, basically. And then in 10.2, we added a hash group by, and the idea there was when sorting is not required, it can be significantly faster, especially for larger groups or larger sets of rows, to do a hash group by. So that was something that was added as far back as 10.2. That seems like a long time ago now, but at the time, it was a pretty cool implementation or enhancement, mainly centered around data warehousing, because the data warehouse folks were doing very large queries against very large row sets. So I have a couple examples. This is just a select statement, just a two-table join, our typical line order table and customer table from our star schema benchmark. If you've looked at any of our previous AskTOM sessions or our examples on our blog, we use the star schema benchmark, which is a large fact table, the line order table, with 4 dimension tables that we use to show examples of how database and memory works. We have our join against the customer key between the two tables. And then we're grouping by region. So basically what I've done is I've selected region. We see we have 5 regions, and I've summarized all of the revenue for each of the individual regions. And so that's kind of the group by part of it. The region column, and then summarizing or doing an aggregation with one of the other column values. And so that's a kind of a simple way to see how a group by actually works and what we're doing with group bys. Then I included a couple of execution plans to go along with detailing a sort group by versus a hash group by. And so it's the same basic query. You notice we have an order by the region. And so in the execution plan, you'll actually see sort group by. So we're doing a hash join, but we're doing a sort group by. So that's how you can actually tell which type of group by you did. Now, since we're ordering the region or by the region, we wind up doing a sort group by, because a hash then would require a hash group by, which I have here, would then require a sort. And since in this case we might not need a sort, a hash group by can be more efficient, especially for larger row sets. So it's kind of the difference between the two group bys. You'll see that right in the execution plan.
So Andy, is it fair to say that if we've got a sort or an order by in the query, we'll always get a sort group by? Or are there cases where a hash group by is still be chosen?
It's a cost-based decision, but in general, if you have an order by, you'll typically get a sort group by. Now, there's a caveat with that when we get into talking about how database and memory leverages group bys, but in the case of just a traditional group by, traditional queries, an order by is going to dictate we do a sort because it's going to be cheaper or less expensive, less costly to take that execution path. So, I have a little difficulty here. There we go. So, since database in memory leverages a new group by feature, but it does so through hash joins. So we talked about hash joins in our previous AskTOM session. So I wanted to do a quick recap of hash joins, since it's going to be so key to explaining how the new join feature in-memory aggregation works with database in memory. So just to recap, we typically, Oracle will choose a hash join when it's joining relatively large amounts of data. It does have to be an equijoin, so we have to have a join key, an equality join key. Made between two row sources, so obviously if you're joining multiple tables, we can join the row source from a previous join with each of the subsequent tables to join between two row sources, but Oracle generally just joins two row sources at a time. And we'll kind of expand a little bit on that, because we saw in our previous session that database in memory is able to cheat in that aspect, and we'll talk a little bit about that. There's typically a build table and a probe table. The build table will create a hash table in memory, and then we'll probe that hash table as we scan the probe table, and that's essentially what a hash join basically is doing. We'll hash the join key in each of the two tables, and we'll compare those hashes to see if we have equality. Database in memory, as we described in the previous session, can leverage a Bloom filter, however, to optimize a hash join, and actually turns a hash join into a scan and filter operation, both on the build table, which is where we'll scan and build our hash table, and we'll build a Bloom filter, which is basically just a bit vector, if you will, that says, do we have membership? Is the join key, does it pass our filter criteria, and are we going to find a match or not? And Bloom filters are probabilistic. Well, basically, we can get, that was a big word, we can get false positives. And so we always have to go back, and from the result set, we always have to go back and verify that the hash keys that we found matches for actually exist and don't involve collisions where we might have gotten the same hash value, but the value that we compared to actually didn't pass the initial build phase of the scan of the build table. That was a mouthful. So, and I had just kind of a hash join summary again, which is what we did in the last session, but the build table, usually the smallest table, again, as I said, we create a hash table in the PGA. It can spill the disk, and if you're interested in the gory details, we have that all documented in the documentation of how and when we do that if we don't have enough memory to hold the hash table in the PGA. The second, or probe table, is then scanned and each row retrieved. We compare the hash join keys to see if there's a match, and then we pass that back up through the execution plan. So we might have multiple tables that all are involved in hash joins. But again, we'll only actually perform the join on 2 row sources at a time. And then we had created a, I guess I'm going to flip over, so I have this great animation that I even improved from the last session. So when we do a in-memory hash join, we scan, again, the build table. So in this case, we have a stores table, which is our smaller table, and we have a sales table, which is our larger table. We'll scan the stores table initially, so that'll be our build table. We'll create my diagram up here. We'll create a in-memory hash table from that scan, applying any filter predicates and picking up the join key. We'll then create a Bloom filter, and based on that, at the same time, if it's an in-memory query, we'll create that Bloom filter, basically deciding do the rows in the stores table pass the filter predicates, and then if they do, we'll give it a value. If not, it'll be a 0, and then that Bloom filter, or bit vector, if you will show up and be passed. Will not show up, but we'll create it and we'll pass it then into the scan of our sales table. Notice that it's just a bit vector. It'll have 1s or 0s. Since we don't have the ability to have a linked list that we have, that's what this symbol up here is supposed to show. It is possible to have hash collisions, so we can have false positives. And then we'll push that Bloom filter essentially as another filter predicate into the scan of our probe table, and along with any other filter predicates. And then any matches are then sent back. We double check the hash value to make sure that we don't have any false positives. And then we'll pick up the actual column values from the join. Since we've been working on hash values, we'll pick up the actual join or column values and pass that back in the execution plan. So that's kind of a quick overview of how a database in memory, traditional database in memory hash join works, because this is very similar to what we're doing, the same basic process that we're doing with a vector group by or in-memory aggregation, which we'll talk about next.
And just to remind us all, there's nothing we need to do special in our queries to get a Bloom filter, is there?
Well, no, there's actually, if you have in database in memory or in-memory underscore size enabled, and so you're using database in memory, the only thing special is that to generate a Bloom filter requires a filter predicate. And so you have to have a filter predicate on, in this case, the stores table in order to create a Bloom filter. Otherwise, we'll do this, but we won't be able to leverage the Bloom filter, so it won't be as efficient as if we were filtering additional rows. I think that answers the question. Oh, and we can't possibly forget, in the case where we can support hash joins with multiple dimension tables or multiple small tables. It isn't just 2 tables as in the previous example. And so I talked about this again in the previous hash join series, but I wanted to stress this as well, because the same basic concept is associated with in-memory aggregation as well. And so the takeaway here is that if we have multiple, say, dimension tables, maybe a star query, so we have date, dim, supplier, and part as our smaller dimension type tables, we still have our line order fact table, we can actually do something, it's not magical, but it's a computer science relational theory, and we can actually we can swap the join inputs and do a right deep tree. Traditionally, Oracle will do left deep trees, and you can certainly go look that up on Google and Google for right deep trees. The gist of it, though, is that now what can happen is we can actually pre-scan or scan the dimension tables without having to actually perform the actual join. So in this case, we can scan the date dimension table, create our hash table in the PGA, and create a Bloom filter. And we can do this multiple times. So we can do this for the supplier table, and we can also do this for the part table. This is a big deal because this allows us now to, when we join with the line order table, to apply multiple Bloom filters to that scan of the line order table. So effectively, this allows us to continue to honor, a scan of of each of the tables only a single time. We don't have to repeat the scan of the line order table for each of the subsequent joins to the date dimension or supplier or part table. We can do all of this in a single, like I like to say, a single pass over the data. We can then actually complete the join by then traversing back up the tree so that we still have to reconcile, since we're using Bloom filters, that we don't have any false positives, and we can pick up our payload columns at the same time so that by the time we're finished with that hash join, we can, or the multiple hash joins that we've traversed down and back up the tree, so we'll return that row set back to the execution plan, fully joined against all of those tables, but with a single pass over each of them and not having to do multiple passes or carry multiple values up through the join tree for that particular join against the line order table. Did I do okay there, Maria? Okay. All right. So that's kind of the background that I wanted to cover, both with group bys, how they work in Oracle, and then with our hash joins, so that all of this is a setup so that we can talk about in-memory aggregation. So let's dive into the nuts and bolts of this. So in-memory aggregation, there is actually a full white paper that we wrote that's available on OTN, or you can also get to that from our blog, the resources page on the blog, which goes into lots of gory detail that we won't really try to cover, although we'll try to touch upon the basic aspects of it. I'm going to show you some execution plans of how this works and what you can look for if you see this in your plans. But again, you won't see a vector group by, which is the new one. So we have a sort group by, we have a hash group by, and now we have a vector group by. That's what it'll show up as in the execution plan. It's kind of covered over this terminology of in-memory aggregation. But we'll touch upon all of these features, and then if you want to dive into this in more detail, the in-memory aggregation white paper is a great place to start, and then of course trying it out for yourself, which is kind of what we're after, motivating you to take a look at this feature, because it is significantly performance improvement over the existing group by. So we'll typically get anywhere from 3 to 8 times query performance over a traditional group by, either a hash or sort group by. Since it works best with all objects populated in the column store, there's essentially no I/O. So that's one of the ways we get a speed up, plus we get to leverage all of the existing features of database and memory, like SIMD vector processing and in-memory storage indexes, and we take advantage of the compression that we get in the column store for the columnar data. And of course, we only have to look at the columns that we're interested in. We don't have to look at all of the columns in all of the data. So we can get significant speed up over the row store, and even without, or even with database and memory, a significant speed up over a group by that you might not be able to take advantage of prior to not having in-memory aggregation enabled. You don't actually have to do anything to enable in-memory aggregation. It is a cost decision that kind of goes along with all of our in-memory features, where we don't expect you to change any of your application code. All you have to do is enable database and memory and populate the tables that that would take advantage of analytic processing. Database and memory doesn't enhance OLTP per se, because we're not going to speed up inserts, updates, or deletes. We're actually just talking about scanning large amounts of data very, very quickly. So what else? So for in-memory aggregation, we do actually, like some of the other features of database and memory, we won't use indexes, but we can also reduce the need or eliminate the need for bitmapped indexes, maybe in a warehouse that you've had to use to get aggregation, summary tables, denormalizing tables, or materialized views. So very often, with in-memory aggregation or with a vector group by, you can operate directly on the source data and get that aggregation performance without having to do anything else, which is actually really cool because it takes away a lot of effort to create the summary tables or maintain materialized views. You don't have to have an index for every different query. Basically, it enables ad hoc type queries right against the source data and taking advantage of performance features to make it feasible to do what we call real-time analytics. In-memory aggregation will scale better because it is really just CPU and memory access. And so that's kind of some of what I think are the key advantages of vector group by. I threw this slide back in. I had originally taken it out because I didn't want to be too slide-centric, but I thought it made sense to add to try to explain or help you visualize a little bit about what we're talking about. So in this case, I have our sales table, similar to our line order table or the fact table, and two-dimension tables, products and stores. And so the idea here is that we're going to do a hash join. We're going to do essentially, if we were using Bloom filters, we generate two Bloom filters. In this case, and I'll explain it in a few minutes, we're going to use something we call key vectors, but we're going to do the same basic processing that we do with a hash join and Bloom filters with database and memory, a write deep tree. We're going to be able to scan both the products table and the stores table, apply the filter predicates, generate key vectors, and use those as input to the sales table. So again, we get to make one pass over the data. However, we're going to throw a little wrinkle into this. In addition to that, we're going to actually do the group by, that aggregation that I showed you in the queries at the beginning. Traditionally, Oracle would have to return those rows or column values and add them up after the fact or during the return of the rows from the scans. But in this case, with in-memory aggregation, we're actually going to do the aggregation during the scan of the sales table. That's why I have that red arrow here. And what we do is we call this an aggregate accumulator or an in-memory report outline is kind of an easy way to think about it. But it's an in-memory area in the PGA that we've basically taken the key values or the group by values, if you will, from the outlet and footwear tables or multiple tables. Essentially think of it as a multi-dimensional array or spreadsheet, if you will. And we're actually going to perform the aggregation during the scan of the sales table. So we're going to stay with our theme of scanning and filtering, joins and aggregations being the key performance benefits of database and memory. And so as we scan the sales table, we'll contribute the group by columns, if you will, to the accumulator so that by the time we're done with the scan of the sales table, we've actually already done all the aggregation to return that as part of the group by query right directly to the as the finishing of tongue-tied again. So we're basically, as we finish the scan of the sales table, we'll have already performed the aggregation, and so all of those results can be returned directly to the invoking query such that we don't have to do any other external processing of that data, which is much more efficient, which is why we get a 6 to 8 times performance improvement over a standard group by query.
So Andy, just so I'm clear, what you're telling us then with vector group by is that not only are we doing the join as part of the scan, which is the benefit we get from Bloom filters, but we're also keeping a running total or the aggregation going as part of that scan as well. So I've got a running total going as part of the scan. I'm doing the joins as part of the scan. So effectively, once I've scanned the sales table, the query's done?
Yes, effectively. So we're all done. So we basically do all of the work in the scan and filtering and aggregation of the in-memory objects. And so we don't have to do any other outside work. And that's kind of goes again with our theme of the ultimate database in-memory query is one that only has to access the objects themselves and can return the results of the query based on that. It doesn't have to do any other external work. So some of the details, again, it's a hash join. We will use a write deep tree so that we can apply all of the dimension tables, the key vectors, if you will, in this case, to the scan of the fact table. In our case, the sales table. The aggregate accumulator will actually aggregate that data as well during the scan. So all of our work is done during the scan operations on each of the in-memory tables. The aggregate accumulator will be kept in that PGA. We'll talk a little bit more about that. Typically, to invoke a in-memory aggregation or vector group by, the dimension tables have to be about at least 10 times smaller than the fact table. That's kind of in order to, the cost, since it is a cost-based decision, the cost of invoking the key vector creation and the aggregate accumulator creation, we basically use that heuristic to determine whether that's going to make sense to invoke the extra work, because we wouldn't want to do that for very small values or very small tables, because we wouldn't get the benefit we're expecting to get out of much larger tables. And again, on that theme, as the dimension tables and the grouping columns get larger, as the fact table is larger, we get more and more benefit. So you'll see more benefit on much larger row sets than you will on smaller row sets, which goes to the fact that it's much more efficient, it scales well. And in addition to that, our 12.2 feature of join groups, we can leverage join groups and the common join encodings that we have in that feature that we talked about a little bit in the hash join session. We can actually leverage that. So again, we're trying to save as much work as possible as well. So if we have join groups against our dimension tables to our fact table, our common encodings of those, or dictionary symbols, if you will, can be leveraged to save additional work and not having to rehash any of the join columns. In addition to that, since we do have to know, so one of the differences between Bloom filters and the key vectors for our vector group by, which I'll show you in a few minutes in some subsequent slides, is that we use a surrogate key because we have to know all of the join column values or all of the aggregate or group by column values, so that we can create our aggregate accumulator in memory. So we're not going to resize or recreate that on the fly. We're going to create that up front. And so we'll use surrogate keys as part of the key vectors. And again, I'll describe this a little bit, but the main difference between a key vector and a Bloom filter is it's precise. So there won't be any false positives. It'll be a little bit larger, but it'll still be a dense memory structure. And it'll map directly to our aggregation accumulator, that area of memory where we're actually doing the aggregations. And I'll show you kind of a demonstration of how that works. And then the key vectors are still pushed down into scan, just like Bloom filters. And again, we're able to then do the aggregation and populate the sum. If we're doing say a sum, we'll be able to populate those aggregated columns into the memory area where we have our aggregate accumulation. In addition, if that aggregate accumulator, since it is in memory, were to grow too big, we do have the ability to fall back to a hash group by and actually take advantage of both. So we can do as much as we can with the in-memory aggregation, and then we can always fall back to a hash group by if that area is too large to fit in the PGA based on any restrictions for, say, size that we might have, or if you don't have enough memory to handle that. So, and I'll show you that in the execution plans where that shows up and how you can actually see that that's there as a backup. And of course, all of this, which I've just gone over very quickly and may have just confused the issue, but I do need to talk about it, is available in the in-memory aggregation white paper. This is kind of a lot to go through, but it's background so that hopefully you'll catch what we're trying to discuss, and then you can try it yourself. Just as a further late materialization, so the bottom line is that we don't carry, so since we're using dense grouping keys and key vectors, we do ultimately have to materialize back the actual column values. Rather than putting them into the join table, we actually keep them in what originally was temporary tables and now is in memory in a temporary structure. We'll see that in the execution plan as well. There was a change in 12.2 where we made it fully in memory, not in memory column store in memory, but PGA in memory. And so I'll discuss that a little bit, show that to you. But basically, it was another optimization we made and kind of goes along with all the other optimizations we've made as we've gone to more current versions of Oracle Database. Another change was that in 12.1, when we introduced database in memory, vector group bys, we weren't as aggressive at picking a vector group by because we wanted to make sure that we were going to get an advantage, basically a cost advantage to using them. Turns out in testing, in almost all cases, a vector group by is faster than any other alternative plans. So we're much more aggressive at choosing a vector group by. If we choose a group or a vector group by and it isn't faster, it's very, almost in all cases, it's only marginally slower. So it's, even if we miss, we're still in pretty good shape, which is why in almost all cases, you'll now see with database and memory in 12.2 or higher, you'll see a vector group by as part of a group by query if it meets all the other requirements. And then last but not least, aggregations on the dimension tables are not supported by vector group by. So then you'll get a traditional either hash group by or a sort group by. If you've got aggregations on dimension tables, which is not typical. Typically you're using the dimension tables as join keys to get a subset of data, and then you're actually doing the aggregation on the fact table. So that's generally not an issue, which is of course one of the reasons that it's not supported, other than it being difficult to implement. So with that, let's go back to some visuals, make it maybe all of this make a little bit more sense. We have our sales table with our fact table as our fact table. I'm gonna move the, oh, I guess I can't. And then we have our stores and products tables, our dimension tables. And so we're gonna scan our, there we go. We're going to scan our stores and products tables. We'll apply our filter predicates, in this case, outlets and footwear. So in stores, we're looking for certain outlets, and products, we're looking for products with a type of footwear. And we're going to then create our key vectors based on that. So previously, in traditional hash joins, we would have created Bloom filters. Now we're going to create key vectors. And so what we've got basically is for each position within each of the two tables, we then have our dense grouping key, or the ID or symbol for that grouping key, so that we know when we hit that in the scan of our sales table, we can validate which group we're going to aggregate to. And we're going to then, based on those key vectors, build our in-memory report aggregator. And so in this case, you can see that we have the values in blue for our products key vector table, and in red for our stores key vector table. And so let's see if we can, I'm going to try to move our pictures so I can, there we go. So in my view of the screen, there are a couple of pictures, are pictures of Maria and myself, and so I can't see the sales table. So, so if we scan the sales table now, we've scanned the two-dimension tables, we've built our key vectors, we've built our in-memory aggregate accumulator. We're now going to scan our sales table, apply any filter predicates, plus we're going to apply our key vectors also as part of the scan. So we're going to see the store ID of 2 and our product ID of 5 with a value of 10 in our first column values that we're scanning in the sales table. So we're going to come over to our key vectors, and for stores, we're going to scan over 1, 2 places, and we're going to catch a 3. And we're going to scan over 5 places in the products, or our key vector for our products table, or get a value of 1. So we know we can go to 1 and 3 over in the accumulator, and then we can put our value of 10 there. Hopefully that makes sense. Then we're going to scan the next column values. We'll see a 6 and a 4. We'll calculate those across our product and stores key vectors, and we'll wind up in the slot 2 and 4, and we'll get a value of 20 there. And then we're going to scan the next value. So 7 and 1, we're going to come across the stores key vector. We'll get a 3, but in the products key vector, we get a 0. So that means we don't have a match. So that means we just skip it. We don't actually have that, as it doesn't meet our group by accumulation. In our next column value, and this is kind of the key to this, is that we hit 7 and then a 2. So now in this case, we actually do have a match. The 7 gives us a 1 for the products side, and then the 2 gives us a 3 for the store side, and we're going to add that. I'm going to go back real quick. So notice it's 10. The value is 10 in that slot, and now when we hit the next column value, we're going to add that 5 that we come up with to the 10 for 15, and that's essentially the aggregation that occurs. But all of this is occurring as we're scanning the sales table, as opposed to bringing all of these matches back into the execution plan and having to do that after the fact or after the scan of the table. So this can give us, again, a 6 to 8 times performance benefit, and we can actually join multiple dimension tables to this. So I don't know if I can get there we go. We got we got the pictures back. Okay, so I can see Maria now in case she has any questions, or if you guys have.
Actually, we do have a question on the chat, Andy. The question was, can we use this aggregation and place tables in memory with OBIEE or any other BI visualization tool?
Yes, of course, because this is all happening in Oracle database. So yes, it's an excellent tool for BI type applications. Excellent tool for any application that's doing aggregations, because since it's all part of Oracle database, you don't have to code anything, or you don't have to say fire up in-memory aggregation, or I want to do a vector group by in your SQL statement, because it'll just take advantage of it on the fly. One of the big things with BI tools is the need, and especially when they're running data warehouses, for things like bitmapped indexes, or maybe denormalized tables or materialized views. Since we can do this right on the source formats of the source tables, now we can eliminate the need to do that. And essentially, in-memory aggregation was developed by the OLAP folks. And so they developed this feature with that explicit requirement in mind. And so it's specifically built for that kind, or basically it's built for aggregations, but BI tools tend to do a lot of that. And so ad hoc BI queries, you don't have to have pre-computed indexes or denormalized tables to take advantage of this.
Great. Okay, so that's good news that this will transparently accelerate or improve the performance of my BI tools. Another question for you, Andy. Do all of my tables need to be in memory in order to take advantage of vector group by?
No, and that's one of the cool features of database in memory. So not only do you not have to have, ideally all of your table would be populated, but even if part of the table is populated and isn't, database in memory will still work. If not all of your tables have been populated in the column store, database in memory will still work, and in-memory aggregation or vector group by will still work. In fact, if you have tables that haven't been populated in the column store, but you're on Exadata, we can actually use this as part of SmartScan. So that's one of the advantages of database in memory and Oracle database in general. All of these features that are available across all of Oracle database are integrated with all of the other features. So you don't have to do something special. You can run this in rack. You can take advantage of parallel query. All of the features that we've been building on, database in memory leverages. So no, you don't have to have all of the tables available. The only key part of that is that you do have to have database in memory enabled. You have to have database in memory for the optimizer to pick this access method or this group by type.
And just so everybody's clear, how do I enable database in memory?
Well, you got to set in-memory underscore size. And so we're going to allocate the column store, and that will trigger the database in memory and the features in the optimizer, the features at the technical, in the database itself, so that objects can then be enabled and then populated in the background into the column store, or not, if not all your objects will fit in the column store in the memory that you've allocated. All right, so hopefully that that kind of makes sense. So then let's see what this looks like in real life, in an execution plan. And so here's the sample query that I've created to use as a demonstration. It's actually the same query as in the in-memory aggregation white paper. So this makes it pretty easy to go back and say, okay, so he talked about these features, and I'm now looking at the details in the in-memory aggregation white paper, and they correspond. And so we've got 3 tables. We've got our time dimension, customer dimension, and then we have a facts table. We have our join keys and a filter predicate on, we're going to look at a specific year. And we have our group by. So we're really going to sum sales and units for the time dimension based on a region. So as we start our scan of our dimension tables, remember the picture I showed you at the beginning where we're scanning the 2-dimension tables, we're going to create our key vectors, we're going to create our aggregate accumulator, and then we're going to scan our fact table, or the sales fact table in our case. So in what we see in the execution plan, I've highlighted in red the access of both the time dimension and customer dimension tables. So we're going to scan, apply any filter predicates, but notice that we also wind up creating 2 temp tables, if you will. And notice that it says cursor duration memory. That was the feature that I mentioned that was added in 12.2. So that even though they look like temp tables, these are really in-memory structures in the PGA. And hold that thought as we move on to the next. So it's the same execution plan all the way through. What I'm doing is I'm just highlighting the different aspects of that execution plan so you can kind of see where all of these activities that I've described over the last couple of slides, where these fall in the execution plan, so you can actually try this on your own queries and see what the value is for having in-memory aggregation enabled. So we're going to create then key vectors based on our scans. So we scanned our time dimension and customer dimension table, and then you'll notice that we're going to do a key vector create. KV is our key vector. We saw Bloom filters :BF in our hash joins with key vectors in in-memory aggregation. We'll see our KVs. We have 2, one for the time dimension table and one for the customer dimension table. And so we'll actually create those key vectors. Again, essentially dense memory structures. We're going to create grouping values or symbols to associate with the actual column values so we don't have to carry that payload through the execution plan. And we'll talk about, again, that was the reason for the creating those temp tables, to capture those values so we can then reconcile them without having to go rescan the dimension tables, because our goal here is always to only touch the data once, to scan and filter that data once and then operate and have all of the operations that we need to do to those done during that time. But notice also that we're able to go through the execution plan and create these key vectors because we have our right deep tree. We've swapped our join inputs. This isn't a traditional execution plan where we're only looking at 2 row sources at a time. We're actually, as I like to say, we're cheating, and we're pre-scanning our time dimension and customer dimension tables, and we're gonna let that flow into the rest of the execution plan. So I will move on. And then we're going to see the new access path, something called a vector group by, and that's in-memory aggregation. So you won't see that until you enable database in memory. And with database in memory, we're going to do our key vector use, very similar to what we see with our Bloom filter use. And we're going to push those 2 key vectors into our access of the sales fact table. Now notice in black I have a hash group by. Well, I don't have it. The optimizer put it in there. It's part of the execution plan. And so that's the fallback. So if the aggregate accumulator, our little picture down below the sales table here, were to get too large, we would actually fall back to a hash group by, and you'll see that in the execution plan as that's the fallback. Now, typically in a normal happy path, we're not going to make use of that, but that's there as a fallback, and so that the query won't fail. We'll just run very similar to when we don't have a table fully populated in the column store, or if the table isn't even populated in the column store, the query won't fail. It just won't take advantage of database in memory for the portions or the table that isn't populated. And the same holds true for vector group by. So the query isn't going to fail if we were to run out of PGA for the aggregate accumulator. We'll just fall back to a hash group by to finish the query. And then we see that we're going to go back. So we've done our scan of the sales table, sales fact, the fact table. We've done our vector group by. We've pushed our key vectors into the scan. The qualifying group by columns have been aggregated. And now we're going to go pick up the column values, since we have only got essentially symbols in our key vector structures. We're going to go pick up those symbols so that when we return from the query, all of the query looks just like it would look as if we hadn't used vector group by and we hadn't used database in memory. So we need to pick up all those payload columns, if you will. Typically in a normal hash join, we'd pick those up from the hash table in the PGA, but in this case, because we can have multiple grouping columns, those values could be rather large, and so we allocated those in these temporary structures. Again, in 12.2, it's still all in memory, and so it's relatively efficient because we're only accessing those temp structures to pick up the actual columns themselves. So it's very efficient. And again, we're still getting a 6 to 8x performance improvement. Wow. All right, we did it. We did it again. We went super deep on you guys. Hopefully that I didn't lose anybody on all of that. But it is an interesting feature, and it is fairly complex. Again, I would strongly suggest that if you follow that or have any further interest in getting more details about that, that you take a look at the in-memory aggregation white paper, where this same basic example is available, and the author has gone through and explained in excruciating detail all of the different parts of that so that you can understand and take advantage of it. Of course, if you don't care about that, you don't even have to worry about it, because we'll enable this and make use of this without you having to do anything. But very often it's useful to understand some of the underlying technology associated with the features that you're making use of.
So Andy, we've got a couple of questions for you. First up, basically, is there any size restrictions? Imagine we've got a data warehouse that's 6 to 8 terabytes in size. Are there any restrictions on the size of the database where this can be used? And I guess where database in memory can be used. So let's start with that one, and we've got a couple of others regarding restrictions as well.
Okay, so actually the only size restrictions are really at the operating system level. Since the aggregate accumulator is part of the PGA, we are limited in the amount of memory we can allocate to a single process. However, since we can take advantage of parallel query, because all of this works just fine with rack and parallel query, and which actually we'll talk about in a subsequent, some of the details of that. But the bottom line is that if you do run out of memory, as far as being able to allocate to a single process, query won't fail. It may be not as optimal, which means you might have to parallelize in order to be able to take advantage of multiple processes and the allocation of memory that each of those can make. So the answer is no, but it may involve invoking parallel query in order to take advantage of that. Now, if you've turned on auto GOP, the optimizer should take advantage of that for you, but you may wind up, especially if you haven't, not everybody enables parallelization, you may, especially in a single instance, need to invoke parallel query if you find in the SQL monitor report, for instance, that you're spilling to memory, or spilling to disk, sorry.
Okay, so no restrictions on the size of the database to use database in memory. If you've got a larger data set that your query is accessing, then make sure you've got enough PGA or enough processes in PGA in order to get the vector group by to be able to operate completely in memory. Right. Okay. Are there any other restrictions? That was the next question. Any restrictions in which scenarios? So I think we probably covered both of them there. I guess we could talk a little bit about the fact that you can be quite selective in what you populate into memory to work around any kind of memory limitations.
Yeah, so there's no other, correct, there's other than resource allocations, there's no other restrictions other than, of course, enabling database in memory in the first place. Yeah, but there aren't any other restrictions. And really what we're saying is that for resource allocations, you just have to work around the physical limitations of your database server and your database. But again, since database and memory scales out with rack and leverages parallel query, you get to leverage that with all of the other features as well, including in-memory aggregation. So obviously, since we're with database and memory, if you're fully populated anyways, really just accessing or utilizing CPU cycles and memory access, scaling that or making that faster basically comes down to parallelization. And so that's just another tool in the toolbox. But other than that, I don't know of any other restrictions to taking advantage of this, which is, of course, one of the big advantages with all the features of database and memory. Anything else?
So the next question you've got, and I'm not sure if these two things are related, but the question is, in the in-memory architecture, how are soft parsing and hard parsing behaving in the case the block is not available in memory? And so I think this is a question, the person asking the question, but they can correct me if I'm wrong on the chat, is assuming the in-memory column store is a cache and not a store. And is assuming that it's possible for a table that's been put into the in-memory column store to be aged out. So do you want to talk a little bit about that, Andy, about the fact what will happen in that case?
Sure. I think the block, whether the block's in memory or not, kind of probably gives it away. So the key aspect of database and memory is that we're populating the entire object in the column store. So it's not a cache, it's a store. And we're actually doing that in columnar format. So this concept of database blocks, which we have in the row store, doesn't exist with the column store. Instead, we have something we call in-memory compression units, which are just a grouping of a large amount of rows or column values, if you will. They start out as rows, and then we pivot them from row format to column format, compress them. And so the idea is that the object will be fully populated and it will stay, but the key, I guess, is that it'll stay populated. Even if you don't get it fully populated, say you ran out of memory, or your object grew past the amount of column store that you allocated, the data that's in the column store will stay there, and we'll access all of that data from the column store, and any other missing, if you will, missing data that's still in the row store, we'll access from the row store. So then we get to the hard and soft parsing question. And so that doesn't change, it's just Oracle database. All the SQL layer, the optimizer basically does the parsing. None of that behavior changes because we're really talking about accessing. The only interesting part to that, though, is that when we're hard parsing a SQL statement, that's the time when we'll actually look at the statistics, if you will, on the in-memory column store. We do have some blog posts that talk a little bit about this. In 12.1, you couldn't see things like basically what we do is we take a look at the number of IMCUs, how many rows are in the column store versus maybe certain rows didn't make it in the column store, so they're still in the row store. So there's cost aspects at hard parse to determining whether it makes sense to access the data from the column store or the row store. And then we materialized those statistics in the alt-tab call statistics view so that you could actually see that without having to do something exotic like an optimizer trace. So that's really the hard parse aspect. Soft parse, well, we've already got an execution plan. Maybe we have bind variables, but none of that behavior changes with database and memory. And so the execution plan's already set. And so I think you're right, Maria. I think the key to that probably is a confusion around treating the column store as a cache, which it's not, and this aspect of, how do I know which way to go based on what might be in the buffer cache? But again, that's not really an issue for us because we're looking at this as far as being fully populated. The contents of the column store in general are relatively static. And then other than some of our new features, automatic data optimization and automatic in-memory in 18C, we're working to make that more self-managing. But really the concept still is that we expect those objects to be in the column store to enable fast, that's kind of the in-memory part of database and memory, to make sure that we can access the data as fast as possible. That was a long-winded answer, but hopefully I caught all of the aspects of that question.
I hope so. Okay, next up, we got a question regarding what happens with OLTP. So the question is, this sounds like, in-memory sounds like it's good for analytics, but how will it affect an OLTP system, or how will it operate perhaps in a mixed workload environment?
Okay, I like to, so actually when I start off my sessions, when I'm talking to folks, I'll usually say, we could have called this the analytics database option or the columnar database option. So database and memory is not focused, or is not going to speed up DML or OLTP insert updates and deletes. Now, we do get some collateral benefits because in general, analytic reporting indexes aren't needed, or most of them can be eliminated. So you can get some capacity headroom benefits from database and memory in a mixed workload environment. But in general, insert updates to the OLTP workload isn't going to be affected negatively. It can be effective positively because we can free up capacity workload. In addition to the index story, just in general, reporting on, or mixed workload environment reporting typically will generate fairly significant I/O workloads. But with database and memory, since we're populating all of those objects in the column store, I have a good friend who likes to say we can deheat the I/O subsystem and actually free up quite a bit of workload. And if you don't believe me, we actually have a demo, a video on OTN that shows an actual OLTP workload that's running, and then we show using a mixed workload environment or reporting activity with and without database and memory. With database and memory, the OLTP workload is virtually unchanged, and this is for a fairly high concurrency rate. And without database and memory, the capacity headroom is significantly impacted, and it does impact OLTP. This is kind of why we say we think with database and memory, you can run analytics in real time right on the source data, because as long as you have capacity, CPU capacity headroom, you should be able to run database and memory queries as much as you want, basically, as long as you have the CPU headroom. Because we're not going to have an I/O footprint. We're not going to be taking any significant locks or latches in order to do that, because we don't have to serialize on the database and memory data, because all of that happens in the row store with your OLTP workload. Another long one. But keep them coming. Keep the questions coming. These are all great questions.
They are all fantastic questions, actually. So that's it for the chat, and we're pretty much at the top of the hour, Andy. So do you want to just let us know what we're going to cover next time?
Oh, I don't even remember what we're covering next time, but to be honest, I was so focused on this, I didn't even think to, let's see, if I go out of full screen mode here, do I have on our, I don't, well, so you know what? I'm not sure, folks, what we could take an informal poll if you want, and just, if you want to put them in the chat, what topics you might want to see next, that would be awesome. Yep. You can always send an email to me. In all of our formats, I always include our slide. My email address is right there. Our blog, by the way, is also there. I think probably what we'll probably tackle next, unless we have a overwhelming majority of topics that folks want to hear, probably tackle RAC. That's probably a good next topic to tackle, and that's actually very interesting. The scale out, the parallel query implications. RAC is a great topic, and so that's probably what we'll tackle next, unless somebody has a better thought or a better idea.
So one last question just came into the chat right at the very end there. Where can we get these slides and all of the links that you've talked about? So
yeah, so the slides are all available on our, the Database and Memory Office Hours page, the one that you actually connected to join the session. And if you just scroll down, you'll see all of our Office Hours sessions, and you can just click on Watch the Recording. And then the other key place would be to go to our blog, We have not only technical blogs, but there's a resources page with all of these links. So we have an in-memory aggregation white paper, or in-memory technical white paper, and of course then the documentation as well. We have in 12.2 and 18C, we have our own in-memory guide, which has a lot of these topics as well. So I guess those would be the areas that I would suggest that you take a look at. We really do try to make all this information available to you. So use either our blog or the AskTOM link as kind of your portal into finding other information. And I think actually at the bottom, I have a lot of those resources linked there as well. So you can really just go to the AskTOM page. It gets you to the blog, gets you to some of our other white papers, documentation, and so that's why I did that, so that you make it easy for you to get to that information.
And if I want to sign up for the next one, because I've gotten a couple of questions in the chat about when is the next one and how do I sign up for that, it's all here on this AskTOM office hours page, right?
It is, and if you've signed up and are watching this session, you're then signed up for life, basically. So you'll get an email when the next one gets scheduled and what the topic is. So you won't have to do anything separate. You should actually get an email when we've scheduled it. We're going to try to do these again. We've been doing them basically once a month, and so it's great that people want to see it again, see the next versions or the next topics that we're going to talk about. And so all of this can basically be done right from the office hours page.
Awesome. Well, thank you so much, Andy, for your time today and for the explanation on in-memory aggregation. The video for this session should be up in just a couple of days, so folks can watch it or share it with colleagues right off of the AskTOM page going forward. And we'll be back June 26th, it looks like.
Great. And thanks, Maria, for all your help as well.
No worries. Thanks, folks.
Thanks, everybody.